One specific technology I'll be talking about is the Fluidized Bed Reactor. So Eugene had shown basically this slide here, trying to get the arrows to move, there we go. And this is a little bit more detailed, just to help you understand what a fluidized bed bioreactor is. And to the left side, you have feed contaminated water coming in, and to the right side, in the green arrows, you have the effluent coming out. It's just a mass balance. But what you have is a recirculation pump, which fluidizes the media, and naturally, hydraulically, I should say, fluidizes the media. And the media has a set specific density. I'll talk about that in a moment, and allows that media to be hydraulically fluidized at a certain gallon per minute per foot squared. We do add in an electron donor. You've heard this a lot today, different electron donors. We've heard ethanol, we've heard acetic acid. There are some other, there's one other NSF approved electron donor that EOSI produces. It's a micro C product. So we add an electron donor in there to get the oxidation reduction reaction occurring for nitrate and other oxyanions. We do add a nutrient source, you see off to the left there. And that nutrient, kind of a one-a-day vitamin, and generally is a phosphoric acid, which can provide a phosphorus source. So inside the reactor, though, what happens here? So we have the system during startup, we expand the bed about 25 to 30%. In this case, I'm talking about a media, which is carbon, activated coconut shell-based carbon. We could also use sand, and there's different reasons why you do that. I'll talk mostly about carbon today, just as an example, but it has a set specific density, mass over volume. And as a microbe attaches onto it, you get a lot of microbes. They're mostly just water, so they don't really add any mass because the particle itself is in a water medium. But the volume expands, so the specific density actually decreases, and what that allows is that the bed will biologically grow, and it expands to about 40 to 60%. And the idea there is then you get a longer HRT and you get more opportunity for treatment over this longer HRT. Now, I get the question a lot, well, how do you prevent the media from just growing up over the top? Well, we have some devices, some patented devices that actually agitate the media, and we can set that height wherever we want to. So that expanded bed up to 60%, we can keep it right there by using this agitation mechanism at that height level. And what that does is it shakes the biomass off the media. The media now has a higher specific density, drops back into the bed, and the biomass will float over the top and out the effluent. And this is where it comes into drinking water to minimize turbidity and some of the aspects of the surface water treatment rule. So some of the advantages of the FBR systems, small footprint, you get a high concentration of biomass on this media for typically plug flow characteristics. So you really get a long solids residence time as the biomass attaches onto this media itself. And the media has macro and micropores, which it can attach to. And so in terms of talking about carbon, sand's a little different animal there. But, and then that allows for you, with that amount of biomass on the media, to have shorter hydraulic residence times. And you can get steady state performance. FBRs can run continuously without backwashing or cleaning operations. It's a proven design. I'm going to show you some examples, but this is over 15 years we've been building this system. We have over 40 systems installed, full scale. Just not drinking water per se, but some that produce drinking water. I'll talk about that as we move along. It's robust, the system won't plug up or channel, and it's tolerant of high feed concentrations if you have a shock load, because you have this recirculating water phase that helps fluidize. You can actually buffer through that recirculation. And I just want to talk about this. We've seen this sort of slide in different incarnations today, but how do the microbes work? And as you move up the redox table, and this is no different than you're looking at a landfill or you're looking at a sweaty t-shirt and a gym bag. It all follows the same redox potential. But essentially, if you looked at this as the reactor, and it's an upflow system, and you got groundwater with a substrate. That substrate is the food source, an electron donor. In this case, I'm going to talk about for drinking water is acetic acid, because that is NSF 60 approval. What you first get is aerobic respiration occurs, and I showed at the base of the reactor occurring. So that's the most thermodynamically favorable reaction, and that's the reaction that the microbes are going to want to attack the substrate and get the most bang for their buck. We're all aerobes, and this is what we do and why we're very efficient macroorganisms. But they have the ability as well, some of these aerobic organisms, to also be able to be facultative, what we call facultative organisms that are able to live in anoxic conditions. They don't need to have oxygen there, but they can denitrify. So they use the same process with that substrate. They take the nitrate and they produce nitrogen gas. And then as you move up the redox table, or down, however you look at it really, you can then have perchlorate reduction, you can have selenate reduction, and then you can also have chromate reduction. And we've had some discussions before in prior talks. I talked a little bit about this. And eventually you'll get to sulfate reduction and methanogenesis, where you really get into anaerobic conditions. So I'll talk about the FBR sizing just to help you understand. What we basically do is we design systems from 1 to 14-foot diameter columns, and they can be anywhere from really 14 to 30 feet tall. And we can also build larger built-in place systems, field-erected systems. But the sizing is really dependent on the loading conditions and based also, I talked about earlier about that expanding bed, you know, how much perchlorate or how much nitrate, we're talking today, how much nitrate you can get removal across that system with that expanded bed. And then we use a model that we've developed over the years to design and eventually be able to size these systems correctly so we're not over-designing or over-engineering them. So I just throw this slide up here to give you some examples of some of the non-potable FBR full-scale systems that are out there right now. And I said we have over 40 installations. Many of these, including the one in the upper left-hand corner, which is out in Henderson, Nevada, produce water that feed the Las Vegas Wash and Lake Mead and the Colorado River. So in essence, it's producing water that eventually becomes potable drinking water. And then there's some other systems. There's one upper right corner is JPL, and then down below in the middle is a facility in Northern California. And so there's a lot of different shapes and sizes, and we're not tied to stainless steel 304 or to FRP. It really just depends on what the client's needs are and what the environment is, what we can provide. I put this system up just as an example. This is a facility down in San Diego at a fuel terminal where they have nitrate. If you've ever been to Qualcomm Stadium where the Chargers play, underneath that is a massive fuel plume that's got underneath the stadium, and they're constantly doing remediation. Well, one of those, after they remove the BTEX and the MTBE, they also have nitrate. And so before discharging into something called the Murphy Canyon Creek, they treat using 2 different FBRs. They did this in series. About 5 years ago, they built one, and then 3 years ago, because they like the technology so much, they built a second unit, and they're able to fully treat that nitrate before discharge. And that doesn't have a filtration mechanism on the back end. I do say, I talked about this a second ago, but the facility in Henderson feeds the Colorado River, and the facility in Northern California feeds the American River. So again, sources of water that are being used for potable supply. So the city of Rialto, I guess it's about 6-7 years ago now, decided to look with us at biological treatment, and they wanted to understand, could the FBR use, they knew they could be used for remediation purposes. They wanted to look at it with us through a grant that we had through ESTCP. It's a kind of a research group, part of the DoD. And what we did is we looked at being able to treat 50 gallons per minute through a biological reactor, a fluidized bed reactor, followed by all the necessary post-treatment. And we wanted to make sure that we self-seeded the reactor with indigenous microorganisms. We didn't add anything. When we ramped the flow up to 50 gallons per minute, and then we were going to look for, in this case, both nitrate and perchlorate removal, and then evaluate the downstream equipment, and do many of the things that were talked about earlier in Eugene's discussion about some of these challenge experiments, starting and stopping the unit, power shutdowns, that sort of thing, and then looking at pathogen determination and disinfection studies. And I put this slide up here just to show you the data. And on the x-axis there, it's elapsed days, and kind of just gives you sort of somewhat of the history of the operation there. But what it shows, the red line is the nitrate coming in. Now the nitrate at this facility wasn't that high. It was about 28 parts per million as nitrate, or 6 about or so as nitrate nitrogen. But what you see there is essentially it's less than 1 or 2 continually. And then after we did some of the feed shutdown experiments, you really don't see the nitrate breaking through. Even you see a tiny little bump there, but not certainly above the MCL. And one of the things you have to understand about biological systems is when you shut them down for 4 or 5 days, if you've just started the system up, and David had referred to this earlier, that if you have a clean system, it's going to take time to start back up. But if you've got a system that has microbes that have been growing for 30 to 40 days and the system's starting to really acclimate, shutting it down for a week and then restarting it, you're going to see minimal amount of breakthrough of that nitrate. Shutting it down for months on end and then restarting it, you may eventually see some breakthrough when you restart it. But with a fluidized bed reactor, with the recycle or fluidization loop, you're able to maintain that biomass in there if you don't have feed water going in by either supplying a sodium nitrate source or some other electron acceptor. David had mentioned oxygen could be possibly provided, but a way to keep the microbes in that system alive and viable. So the data here I just wanted to show you was just sort of the continual over about 235 days or so, less than certainly the MCL and near non-detect or non-reportable at all times. So the conclusions were, with the indigenous population, the seeded system had full nitrate treatment with about 21 days of startup. And actually, for both nitrate and perchlorate, again I mentioned, because that was also another oxyanion we were looking at, it met all MCL standards and was using a forward feed control logic, meaning that it would look at what the load of contaminant of nitrate was coming in, and then it would add just the right amount of electron donor so that you would just kind of like ride the razor's edge and get just the amount of treatment you want. You don't have to go to non-detect. That's the other thing with biological systems. You can go, if you've got 100 parts per million, go down to some level and actually if you want to go down to 20 parts per million, you can do it by adding just enough electron donor. So there's ways you can operate the system such that you maximize your treatment performance and minimize your cost. In terms of the challenge experiments, once the system was grown a bit after about 20 to 30 days, and when we had a shutdown experiment, the rebound was as low as 2 hours, but it didn't exceed the MCL. And then I just put a paper up there. If you're interested in learning more about that particular experiment, you can look at the AWWA paper from a few years ago. So what did this do? In 2009, working with the City of Rialto and West Valley Water District, we designed a 4,000 gallon per minute FBR drinking water plant. And this plant was to mimic on the backside an existing surface water treatment plant. And the idea behind that was that we really just wanted to put an FBR in front of the surface water treatment plant that the operators were already knowledgeable in operating. So we didn't want to shake their world too much by just having an FBR in front of the typical downstream surface water treatment plant. So the process train was two 14-foot diameter FBRs, 24 feet tall, and then two 12-foot diameter aeration vessels. And there's other ways you could do aeration as well. Two Siemens Trident filters, and the question was earlier, what types of filtration can you possibly use? Well, there's continuously backwashing sand filters, there's multimedia filters, there's membranes. We went with this particular series of process technologies because this is what the operators had been utilizing at that surface water treatment plant. Again, we just wanted to mimic and try to minimize the stress on their operation. And then a chlorine contact chamber based on the results we showed at CT of 4 at 4,000 gallons per minute. Again, this plant was designed for 4,000 with all the infrastructure for 4,000 GPM, but we're starting with 2,000 GPM with two of the FBRs. And then a DAF for solids processing, and then this also had online perchlorate and nitrate analysis system, which then feeds to a reservoir, which will go to distribution. And here's a photo of the full-scale plant in its glory, and I need some fanfare, I think, when I see it, because it's, like, again, about 12 years of my career to get this plant built. But what this system is, and I just want to run through it real quick, is I'm going to run through this part of the slide. You have feed water going into the FBR. You've got the fluidization pumps there, fluidizing the media. You've got chemical feed that feeds into that fluidization line, which is your electron donor and your nutrient. And those are the chemicals that are being added. Once that water passes from the FBR, it goes to the post-aeration, because remember, in the FBR, it's an anoxic process. Oxygen's been removed. You then re-aerate the water, and you get it back up to an acceptable DO level, and you have some blowers that can provide that. You then go through filtration, and these are the Siemens Trident filters. You have a backflush for that system with some backwash water that can go to the DAF, which then you can handle your solids. The idea there, just so you understand, was to be able to recover about 99% of the water by doing this. If we didn't do that, we'd probably recover about 95% or so. So going with the DAF is able to get that last few drops of water back into the feed of the system, and that's what this shows here. After the DAF, the solids are pulled out and the water goes back. It no longer has nitrate in it, so it can go back after the FBR. It doesn't need to be retreated. That goes to a solids. The solids go to a small tank that are fed directly to the wastewater treatment plant with the City of Rialto, a POTW, that take that and add it to their aeration basins, essentially. And then there's some sampling, online sampling that we do. Finally, chlorination, and then out to the reservoir. And so that's the entire plant right there, and it will soon be open to the public for tours if you're interested. And again, it's right where the 15 and basically the 10 freeways intersect, right in that area in Southern California. So I took this and I said, okay, I wanted to understand, the DPH had asked us to take a look at the applicability to small communities, and how can a biological system be utilized in a small community environment. You know, issues that you look at, and even when I sit back in the audience and I look up here and you see a lot of these unit processes, you think about, okay, you downsize that system, but you think about, well, still, what are the cost implications compared to, say, ion exchange? Or other electrodialysis technologies or membrane technologies. And then what's the operator attention required? And then what's the robustness of the technology? So you look at all of these different issues as you go to much smaller communities. And we were asked to take a look at a problem definition of 50 gallons per minute, 60 milligrams per liter of nitrate, and treat to about 30 to 36 milligrams per liter. And so what I looked at it and I said, okay, I want to have a continuous water flow, if possible, if that's the example we're given. And so have a 10,000 gallon feed tank that will allow you to feed that system continuously. Is it absolutely necessary? No, but it would allow for possibly less instrumentation and also allow for you to have a continual feed stream to the system at all times. So when I size this out, it's about a 3-foot diameter FBR, 16 feet tall. You can have various forms of back-end filtration and chlorination, and there's some various options that you can employ. And probably you want to look for the cheapest one, I imagine, the least expensive, but you also want to have the least expense and the least amount of operator attention, certainly. So that's something that we've worked with in many applications, and so we kind of bring that expertise. But at the same time, the utilities sometimes want to have a specific type of filtration or downstream chlorination or disinfection mechanism implemented. So looking at the capital costs for a small system like this, and I give you an example that you see right here. This is actually the demonstration that was a Rialto. That's a 3-foot diameter FBR in the foreground, and then you see a couple other tanks. There's a post-aeration tank in the middle. Off to the left is what we call, that's a small trimite filter. It's kind of the little cousin of the trident filter. And this is feeding, again, 50 gallons per minute and treating at 50 GPM down to, in this case, down to non-detect for nitrate. Materials of construction can be steel, can be FRP vessels, and it depends if you want to do PVC Schedule 80 piping or coated steel. Just depends on what you're looking for and how your costs are all associated there, and then what control logic is required or necessary. And then the filtration and chlorination for this type of system can add another $75,000. And so if you look at the all-in cost, you're probably somewhere in the order of about $300,000 for the equipment. Now, they've asked us to use a 1.5x cost factor for installation, which I think is actually pretty high for this system. But if you add that all up, you know, it can get pretty expensive. And so now you're into it for about $450,000. The operating cost, and again, I want to make sure when we talk about comparing operating costs from prior presentations that we're all really comparing apples to apples. I look simply at what chemicals are required. All biological systems are going to require labor, so I've kind of pulled that out, and they're all going to require electricity, so I've sort of pulled that off to the side. I'm just looking at the chemicals, but it's about $330 per million gallons treated, or about less than $110 an acre foot. And if you look at some of the prior studies we did when we did the original demonstration, I think the numbers we had were right around $125 an acre foot for treatment for some larger systems. So they falls within line of what we've provided in the past. And then you have some solids generation, I'd say about 4 milligrams per liter for this, again, this specific application, treating 50 gallons per minute. And you have some backwash water. And now that can be disposed right to the POTW, either trucked off or discharged off if you're local to a POTW. And then the operator attention, I say, is about 3 to 5 hours per week minimum. That doesn't include sampling and analytical. If that's required, there's going to be additional time associated with that as well. So where are we with the state of the art for the FBR technology? Again, about 15 years of data to build on in terms of consistent contaminant treatment of oxyanions and the modeling that we've done. consistently can show treatment down to non-detect if that's what's necessary for nitrate treatment. These are fully automated computer online systems that we can dial into, so operators don't have to be there 24/7 certainly. Really they need to be out there to make sure the electron donor tank is being filled and the nutrient tank is being filled, and to maybe take a few bed measurements and that sort of thing. One of the things I haven't harped up too much about is the ability to handle co-contaminants, though, and things like selenate and chromate. Chlorinated solvents is typically an anaerobic phenomenon, not an anoxic phenomenon. It requires longer HRTs, but there are ways to use this technology in series to be able to have one FBR treating chlorinated solvents followed by another technology treating, another FBR treating another co-contaminant. But within the same reactor, you can treat things like selenate, chromate, and as well as nitrate and perchlorate. And we have data to show that. We just completed a study with Kennedy Jenks consultants at the City of Davis, demonstrating this, the applicability of chromate treatment with the new MCL coming out our draft MCL coming out from the DPH. And then we've really developed and refined the sizing and the electron donor dosage. And I will say that when we built these systems 15 years ago, we haven't changed the design 100%, but certainly we've enhanced it and refined it, I would say, by about 30%. And so what we built 15 years ago is not exactly what we build today. You know, it's just a maturation of the technology. And for the small communities, though, we can build these very small systems, and one up top that you see is the city of Barstow in the photo there, and that's also a 3-foot diameter reactor with a small Connex box, and that's the FBR technology right there that could be used for 50 gallons per minute. Depending on the nitrate loads, you could actually maybe get even a smaller column. You still got to go to filtration and disinfection, though, and that's kind of critical to realize that. And there's a lot of different ways to do that, and it's been proven again and again in other water treatment facilities. So for us to, I think we've been able to demonstrate the efficacy and the applicability of the downstream technology in combination with the upstream FBR technology with some of the past studies that we have done. But with small communities, there may be some additional work necessary in order to ensure that when you have this constant stop and start, potentially, if you don't have a continuous feed, that you still can get continual treatment of the nitrate. So with that, I'd be happy to take any questions. I know I talk quickly, but I'd be happy to go over anything else if there's any comments or questions. Thanks.
There's one up there. Okay, and then we'll catch you.
Yeah, again, Paul Boyer with Self-Help Enterprises. Because carbon is involved up front, have there been any issues with disinfection byproducts on the effluent water?
Yeah, so that's certainly one thing that we looked at when we did these various studies. Because of the 80-60 rule for TTHM and haloacetic acid 5, we looked at that, and what we showed was that never exceeded coming off the FBR. We try to minimize the residual amount of TOC, and that's based on how we modeled the electron donor to be added on that feed-forward feedback control logic based on the amount of load of nitrate going into the system. So we just try to ride that razor's edge to provide just enough electron donor, the stoichiometric amount, plus just a little extra for biomass formation. And so what's coming off the residual TOC, if not, well, and I'll tell you the results we saw of that were still well below the 80-60 rule, but you also have the post-aeration, which has organisms that come off the FBR, which can then oxidize that residual TOC because they're facultative, meaning that they can live in an anoxic or aerobic environment, and they'll actually oxidize any residual TOC potentially there before it's chlorinated and creates disinfection byproducts.
Jim Gesselbrock, Waterworks Engineers. Can you expand a little bit, if you can, on the patented shaker technology you have at the top of the FBR?
Yeah, it's something called the biomass separator, and really what it is it's using air. It's a chamber that will pull in, so you set the chamber down into the height of the reactor where you want the bed to expand to, or multiple. You may put 2 of these there. And what it will do is as the bed rises up biologically, it'll hit that chamber, and the air will essentially suck that media into this chamber, shake it and agitate it, then release that. Now that the biomass is off the carbon, we'll release the carbon out, and the carbon just settles back down and starts a cycle. It drops to the bottom of the bed. The biomass, now with the water, same essentially density, will just float out the top over the effluent and then be caught by the downstream filter. So that's really the patent process behind it. We also use in-bed eductors at the base of the reactor, if necessary, to be able to break up if there's high oxygen areas where you may get more biological growth, and we can use that to break up that biomass as well. That's just basically shearing force, which occurs there.
Another question or two, and then we've got to get back on track. Nope, we're getting back on track then.
Okay, thank you.
Thank you very much. So next we have drinking water test at West Valley Water District site. Peter Hall, thank you.
Again, thanks for inviting me. Really was looking forward to having this discussion with people and listening to some of the earlier talks. I'm really glad I was invited because there's been a lot of good information that's come out. And we want to go up. What was the up on this one? I'm just going to hit. Oh, hidden. Got it. By the way, we have just recently submitted our challenge documentation to the department. And so what I'm going to be talking about is what we are doing in a non-potable application until we do have permits. We did a one-year challenge program also for EPA under the site program. And that was a number of years ago, but this more recent had a lot more design input from our work over the last couple of years. Again, real simple. Again, the whole idea the bacteria consume the oxygen. They're breathing it. What we do is we force them to take the oxygen off of nitrate or some of the other materials. But one of the things that we, in our design, based our system on was work that was done primarily by the Japanese to improve the essentially performance for existing wastewater treatment plants. And they found that by using a carrier to build the bacteria and circulating that bacteria in a constantly stirred reactor, they got enhanced performance of the system. And I'm going to speak a lot today about the control techniques that we used, our control technology, because that was really the key to safe operation of our system. And one of the keys to any of these is what are you doing to protect the effluent coming off your system? Now, the first item this is work that was done primarily in Japan, was showing that a constantly stirred reactor can get high efficiency. And the reason that was very simple. You're not changing the environment for the bacteria. They're seeing a constant environment, and bacteria don't like, and I'm a mechanical engineer, not a microbiologist, but the bacteria don't want to see change. And so if you have a reactor which is more or less a constant steady state, that improves the efficiency of the reaction. And again, under startup conditions that a lot of people have talked about, if you take the bacteria that are naturally occurring in the well, send them off to your microbiologist, and he cooks those guys back up and gives you a essentially very concentrated stream of the bacteria, your startup is a matter of days. It's not a matter of weeks. Again, one of the things about efficiency that's important is high efficiency means good utilization of the electron donor. In all of the discussion you've heard so far, the key to minimizing waste is optimizing the use of your electron donor. Any additional electron donor just becomes additional biosolids. Another concern in some of these reactors is sulfate reduction, and again, our system has always operated in a positive ORP. And one of the other concerns that Eugene talked about and others is off-spec discharge. What do you do to prevent having material leave the site that is not in compliance? And we're going to talk about that. This one, we lost our full view. Perfect. Try it again. We lost one, but essentially what we're doing in our reactor is circulating these little croutons, as Eugene again talked to them. Essentially, these are a substrate, a surface media for the bacteria to grow and live on. And what we're doing in this reactor is we force the circulation of these little croutons in a circular pattern within the reactor, but also what's happening, and this is all being stirred hydraulically. What we're also doing is, as the bacteria produce nitrogen gas, the little croutons want to go to the top of the reactor. They're trapped between porous plates in the reactor, and we force them back down the center tube. So what we're doing now is continuously cleaning the reactor and the sponges and keeping them in a high concentration. And I'm going to go in a little more detail on this, but essentially what we want to set up is, if this system fails or is challenged, we want to set this thing so it cannot fail in a mode that will allow the discharge of off material. And then also you'll see, as part of this design, I use a recycle, very similar to some of the things Todd was talking about. But the recycle is a very important part of the system to make sure that we get through startup and shut down in a safe environment. So this flow diagram shows the system as designed, and hopefully I got this. So what we're doing is we're taking water from the well. We go into, well, if I can get this guy, go into a deaeration tank where we take the oxygen out, force the bacteria to eat the oxygen off the nitrate, go into the bioreactor, go into a discharge tank, and essentially at this point your denitrification system is complete. You've taken the bacteria and made them produce nitrogen gas, and you reduced all your nitrate to nitrogen gas and water. Again, the next series, again, sorry about the shakiness on this, but again, what we're doing now is we're adding a coagulant, a disinfectant, and going into the post-treatment phase. And the post-treatment phase of the work will go in a little more detail. This shows, again, this is the control system as seen on the site. And in this case, I'm looking at my controls and my valves and how I can control this system. Now, this control system is also set up to be remote. So I can log on, or anybody's got the code, can log on and control the system and see what's going on. Furthermore, if we get into an alarm, we'll get a call telling you your system is in problems. Go take a look, see what's happening. So again, we're not trying to have a continuous servicing of the system. It's serviced whenever you find you've got to add coagulant or other material. But for example, in this case, set point is not to exceed 1 part per million nitrate N. Also in this scenario, if I can ever find my arrow, at the lower, in your case, the lower left-hand side, you see the turbidity as 0.3 NTU. And if you're exceeding that turbidity, it's not going to allow water to leave the system. Now, Eugene again showed a small Hall reactor. We're going to show another picture of the one we had on site, which was a small reactor treating only 3.5 to 5 GPM with a residence time of 10 minutes to 15 minutes residence time, and taking nitrate anywhere from 15 to 20 parts per million nitrated N to less than 1. In this picture, you see 2 arrows. Those are referring to 2 Hall reactors on a full-scale system operated here in California. And this system was considerably lower flow rate than the normal ones that we were looking at where in these size reactors we could be treating 1,000 GPM. But in this case, what we were treating was nitrates, perchlorates, hexchrome, and selenium, and over 2 years of operation, only at the very last test did we actually exceed a selenium standard of actually at 5 parts per billion, and we actually had 6 parts per billion. Hexchrome was taken to non-detect, perchlorates were taken to essentially from 600 parts per billion to non-detect. So these are some of the stories of some of the systems we were operating. The one in Bendina, Kansas was the one under the EPA site program. We ran a perchlorate demonstration on water at Edwards Air Force Base for perchlorate. We ran some tests also for our friends in Rialto, done a number of systems. And again, one of the things that we were asked to do at 3 of the sites was we put our reactor inside, and the system that you'll see that ran at West Valley is in a trailer. And if you have production of sulfate-reduced products, you don't want to run it in a closed trailer. So I think we kind of confirmed at those sites that, yes, we could do the system. Another key part of this is, again, small system design. A small system design is going to have fail-safe operation. And again, going back to what we did on our control system, was that system was totally fail-safe. We were asked to talk about costs, and this really is a difficult thing for us to address in a forum like this, but essentially a biological process is always going to be the lowest cost system, even when you have to do extensive post-treatment controls. And a basic denitrification system, if you just look at what we had in the trailer with a sand filter and disinfection, we're talking the same numbers that other people have been talking. You're talking anywhere from $190 to $200 an acre foot. But that's, again, not meeting all of the requirements that are being addressed in a potable application because, frankly, we haven't delivered a system on a potable application. Post-treatment is going to add to that cost. And what's that cost going to be a function of? Again, the efficiency of the system, the electron donor. The work we did for EPA at Bendina, we used methanol as an electron donor. Methanol is a great material for filtration. We were not going to be able to operate a methanol system in California. So that dramatically changes the filtration requirements of the system. And they're all interactive because as you change the efficiency of filtration, you change what's going to happen in terms of the disinfection. And when you change the electron donor, you're going to change across the whole system. And I think we found the majority of the work that we were addressing at our site in West Valley was focused on getting the turbidity to that 0.3. And everybody says, hey, that's being done on all these different post-treatment systems across the country. But believe me, most of the time we spent out on that system was not removing nitrates. It's addressing the concerns of the post-treatment and getting the turbidity where we wanted it. So what are we doing right now? We'll conduct additional tests as required by the Department of Health to get into compliance with their requirements. We are going to secure acceptance of the system. We have a number of people who are very much looking for low-cost removal of nitrates. I mean, when we talk the dramatic difference for a biological system versus trying to optimize some of the other systems, it's just not in the same ballgame. And then what we want to do is, we've already talked to a number of sites. They're very interested, and they're going to be talking to us once we have our permits. And I'm sorry, Eugene, this one wasn't on your report, but the last one, This is the system that we had at West Valley. All of the controls and denitrifications was in the trailer, and what you're seeing in the back end was the filtration system, and the tail was wagging the dog.
That's it?
That's it.
Thank you. Questions?
Thank you. Mindy Boley with the City of Vacaville. And I was just wondering, you had a non-detect on the perchlorate and the hex chrome. What were the levels to begin with before the treatment?
Okay. Hex chrome was bouncing somewhere around 25 to 40 parts per billion. Perchlorate was running anywhere from 250 to 600 parts per billion. But those were big vessels designed for pretty good flow rates. Maximum flow rate on that system was designed for 150 GPM. So that's why I'm saying if you take those big vessels and you're using them for nitrate, you could put out a lot more water through it as long as you don't have those kind of contaminants. We also had to put in selenium removal, and we were taking selenium from approximately 25 parts per billion naturally occurring to under 5.
Where was that project?
That's outside of Gilroy, California,
Okay, thank you.
and it was a remediation project, and we were discharging water into a navigable stream. You could jump over the stream, but it was, quote, a stream.
Other questions? Okay, thank you.
Thank you.
We're back on track. The next presentation is Jess Brown, Efficient Destruction of Multiple Groundwater Contaminants Using the BIOTTTA System.
All right, thanks very much. You're in the home stretch. I'm sure everyone's saturated with microbiology. Just a couple talks left. But I personally, and Todd and some others referenced this, it's pretty exciting to be here. A lot of us have been working in the biological treatment arena for a while for drinking water, and to see kind of the trends and interests, not just here, but in publications and other symposia by AWWA and elsewhere. It's really exciting to see that it's starting to really, I think, make its way. So I'm going to talk with you about a slightly different technology, but an old school technology, a fixed bed biological system. Begin by going through some of the fundamentals, brief history. I'll show some treatment performance slides, and then finish up with the implementation and costs. So we've seen this today. We're trying to leverage naturally occurring bacteria in the groundwater that are going to use oxygen, nitrate, perchlorate, chromium, other things in the water. Most bacteria can't do all of those things. You need a mixed community to handle all those contaminants in most cases. But in the real benefit overall of the biological process is converting these contaminants to completely harmless end products. So, as I mentioned, fixed bed biological technology. This is old school granular media filtration, where you've just got sand, GAC, anthracite, old filter with that's stationary inside a vessel. You keep the chlorine off that vessel and out of the feed water, and within a matter of days, you've got your biological denitrifying activity. The fixed bed biological process was approved for perchlorate and effectively nitrate back in 2004. As Eugene referenced earlier, in 2011, the specifics of that post-treatment requirement, and I thought it was summed up in the previous presentation really well, that post-treatment becomes an important part of the overall biological process. So to have the details, the specifics of what we have to do to this water after we treat it biologically was very important for developing the system that we use, and that's a biologically it's a biologically tailored two-stage treatment approach. It looks like this. I don't know if this is going to show up. Not at all. It's just a two-stage system, so if I could draw a control volume around it, the BIOTTTA process includes the addition of your acetic acid or phosphoric acid up front. Goes into your anoxic bioreactor where you remove nitrate, perchlorate, other things, and I'll show some data on mixed contaminant groundwaters. Coming out of that system, you've got to add your oxygen back in. You can do that a number of ways. Aeration has been talked about the most. We use hydrogen peroxide. That does a number of things for us. It re-aerates the water, also gives us some oxidizing capacity, and it's also extremely efficient at degrading the EPS, or the slime that bacteria tend to produce when they reduce contaminants. Sometimes you do need a degas. If that nitrogen gas, the nitrate levels are high, you have to remove nitrogen gas, otherwise it binds your system. And that can be done in a number of ways. Cascade type aeration, it can be done with an inline degasifier, cyclone type degasifier. We put a little polymer in to basically just condition the cells that are coming off the anoxic bioreactor. And then we go through an aerobic biofilter. We intentionally leave this system biologically active as well, so it can do a number of things for us, polishing that water biologically. The BIOTTTA system, we have pilots that range from a half a GPM to 25 GPM. The one in the top there is our 25 GPM system. This is a full treatment. This has the 2 stages of biological treatment. If you want to degas just through cascade aeration, that's what the center column is. All the chem feed systems and control inline analyzers are over here, backwash tanks, and then it has a chlorine disinfection step on the back side as well. Our more recent BIOTTTA systems are a little bit smaller and don't include the disinfection step. This one's a half a GPM to 2, and then this one right here, that's 2 to 6 GPM. And all of these systems are designed to be operated like a full-scale system. They're fully operated. The controls are set, connected to the inline analyzers to feed the acetic acid based on algorithm and the concentration of contaminants coming in and the concentration of contaminants coming out. So these are fully operated. We can monitor these. We do monitor these. I run all these pilots. They're actually all in position right now in different parts around the country. I can run all of them from anywhere in the country. We have somebody on site to keep the chem tanks full. History of BIOTTTA optimization, it goes back to '98. We spent a long time bench testing this. This was a part of my graduate work. Pilot scale optimization has been going on since 2002, most of them in Southern California. And you see a range of contaminants there, perchlorate and nitrate, certainly the target contaminants in most of these groundwaters. But we also have some VOCs in some of these waters. DBCP we tested at Western Municipal Water District. In Minnesota, a pilot's running right now that's targeting nitrate and manganese. That's removed in the second stage of that process. We're going to be starting up a pilot later this month in Southern California that's focused on very high concentrations of nitrate, about 170 milligrams per liter. But it also has high concentrations of TCE and TCP in this water. So we'll be looking at removing those contaminants as well. We don't have full-scale installations at this time. We are under a conditional contract at Lincoln Pipestone in Minnesota, pending the results of the pilot study and approval by the Minnesota Department of Health for that system. That would be a 400 GPM system that we hope to have online by the end of 2014 or early 2015. At Todd's site, you mentioned there's that system down there at West Valley is a fluidized bed reactor system. We do have funding in place for a 2,000 GPM system, DOD funding, I should say. We still need the second half of the funding to actually build a fixed bed system in parallel with the fluidized bed system there. So just a little bit on treatment performance. Very, very short contact times needed. All the data that I'm going to show you come from different pilot studies. This one in Southern California, where we're treating about 75 milligrams per liter of nitrate. You see the MCL line there, and our online analyzer is pegged at 5 milligrams per liter. We did run some hydraulic challenge tests down here, where we changed the flow rate at 15%, and you see that it bumped up for a little while and then came back down, settled back down to our detection limit there at 5 milligrams per liter. We've run a lot of hydraulic challenge tests, and that's really kind of the focus of a lot of the testing that we do is we take different stress conditions that we might see out in the field and make sure that the system can handle it. Another one is what happens if your nitrate plume changes? If suddenly you've got another 20 parts of nitrate in your water. Do you have to resize your system or add on vessels? What we were coming in at here at 75, for the most of the study, then we spiked in an additional 25 milligrams per liter of nitrate. In that case, we just adjusted the acetic acid to account for the additional nitrate removal. Didn't change any of the contact time, and you see that there was no blip at all in performance. And this wasn't that surprising, because as you measure that nitrate concentration down the depths of the bed, which we run with about a 5-foot bed depth, we see the nitrate removal happens in about the top 18 inches of the bed. So it wasn't surprising to us that we had additional capacity at the bottom of that bed. What happens if your acetic acid shuts off, your chem feed pump fails? We did a number of simulated shutdown tests in a row here, where we shut the acetic acid off for 2 hours, 3 hours, had a system shut down because of the full plant operation in the middle of that there, and shut the acetic acid off for a 9-hour period. Pilot ran dry on accident. The equalization tank up front ran dry. And you can see through each case, you see a breakthrough, of course, of the nitrate, but also when we turned the acetic acid feed pump back on, which was at the top of each of those peaks, you see that nitrate removal come back very quickly. So no long-term inhibition of nitrate removal with a short-term shutdown test. What about perchlorate? A lot of co-occurrence of perchlorate. And you can see the blue line there is just step changes, step increases in the feed perchlorate concentration from our background, which was at 55, bumped up to 100, 400, 600, almost a milligram per liter. In this case, without changing empty bed contact time or changing the acetic acid feed concentration. And you can see that the perchlorate coming out of the system was very, very low, less than the 6 micrograms per liter MCL in California. Now, over the last year, we've run the BIOTTTA system at bench scale, starting with some groundwater and, from